Optimisation is probably one of the most useful things we can do in maths, particularly if you end up in any kind of design or engineering sort of field later on. So we've got a really sort of simple trivial example here, but it will serve our purpose. So we've got a closed tin, and obviously that means that we've got a base and a lid on it, and it's made from 600 pi square centimetres of tin. What's the maximum volume it can possibly be? Okay, well, a tin, thinking about a can of baked beans or something like that, looks like a cylinder. So we can talk about its radius and its height. Now, we're talking about an area here, centimetres squared. So we need to think about the surface area of this tin. So the lid and the base, they are circles, radius r, and obviously then there's a lid and a base, there's two of them. And then if we take the curved surface and roll it out, we end up with a rectangle that is height h, and the long length is the circumference, so that's 2 pi r. And that is our area. Now, we're making an assumption here. We're making the assumption that we haven't had to waste any of our 600 pi square centimetres. So that area is just the area of the tins that we've used there. So I can say, well, area then, 600 pi is equal to this equation. And the reason I'm doing that before I've even looked at the rest of the question is I don't want to get stuck in the wording of the second part if there is maths that I can be writing here. So area of a circle, pi r squared, and we've got two of them, so I've got 2 pi r squared, and then this rectangle here is 2 pi r h. So this is a mathematical equation that represents this first statement. A closed tin is made from 600 pi square centimetres of tin. I've done it mathematically. What is the maximum volume this tin can be? Right, so here's a keyword, maximum. We're going to be maximising our volume, which means I'm going to need to think maximums and minimums, which means I'm thinking stationary points, which means I'm thinking differentiation. So hence why it's tagged on the end of the differentiation module. And we're thinking about the maximum volume. So I'm going to need an equation for volume. So volume of a cylinder is pi r squared h. Now if I want to maximise this volume, I need to differentiate. But we've got a problem. And our problem is this h. Both the radius and the height of the tin can vary at the moment. We can make it wider and therefore probably sort of squatter, shorter, or we can make it thinner and taller. So both the radius and the height are varying, which means I can't differentiate at the moment. I haven't got an equation in terms of a single variable. I'd need partial derivatives or something equivalent to get rid of it. Luckily, I have an equation that I made just a minute ago, which has both r and h in it as well. And so I can use this equation to get rid of the h in the volume formula. So let's go about rearranging that equation that I've written initially. So 600 pi, I'm going to pull the minus 2 pi r squared over, because that doesn't have a h in it, and that leaves me with 2 pi r h. And so h is 600 pi minus 2 pi r squared over 2 pi r. I'm going to cancel a few bits at this stage just because I don't want to do any more cancelling than I need to later on. There's pi in all of the terms, so I can get rid of that pi there. And I can divide everything by 2. So that goes, that will go, and that will turn into a 3. So that leaves me with 300 minus r squared over r. 300 minus r squared over r. That's what h is in terms of r. Okay, so we've got our volume formula, and we've got this sort of variable that we want to get rid of, this h. But I now know from rearranging the other equation that h is 300 minus r squared over r. So I can substitute those two together and get rid of the h in the volume equation. So volume is pi r squared h. h is 300 minus r squared over r. Okay, one of those, the r on the bottom there, we can cancel with one of the r's outside the bracket. They just multiply and divide. That's all good, leaving me with volume equaling pi times r times 300. So let's rewrite that actually as 300 pi r minus pi r cubed. And now I can differentiate this. Don't forget, I want the maximum volume. Well, maximum to me is a stationary point, and that is where the derivative of a function is equal to 0. So my function here is v in terms of r. So when I differentiate, I will be notating it dv dr, and that's really important. You shouldn't just write dy by dx or something like that, because it isn't. You're no longer y in terms of x, you are v in terms of r. So that's what your variable there should be. So dv over dr is 300 pi minus 3 pi r squared. And we want to know where that is equal to 0, because that's a stationary point. So 0 is 300 pi minus 3 pi r squared. If you rearrange that, you get that r squared is equal to 100, and so r is plus or minus 10. Okay, good. R is a radius, so it can't be less than 0. So r is greater than 0, therefore r is 10. Now I could test my stationary point. I could use the second derivative. So if I do that, I'm going to get that d2v over dr squared is minus 6 pi r. And when I substitute r is 10 in there, I'm going to get less than 0. And so that is indeed a maximum. Great. So we found the radius for this tin. Now, it's actually asked for the volume, so we absolutely cannot forget to do that. It's asked us what is the maximum volume it could be. And this is 2 marks at the end that people think, oh, phew, I'm done, I found my answer. And they actually miss these last 2 marks. So, just substituting the value of r back into the equation, that I guess doesn't have h in it, there's no point. So back into this equation here, we're going to get 3,000 pi minus 1,000 pi. And so the volume of my cylinder is 2,000 pi.